These are the problems that we solved dealing with light interference phenomena, which aligns with chapter 17 in the textbook. So the first couple of problems are about the double slit experiment. This one reads, monochromatic green light of wavelength 550 nanometers illuminates two parallel narrow slits that are 7.7 micrometers apart. Calculate the angular deviation of the third order bright fringe in radians and in degrees. And if we want the fringes to be 1.5 millimeters apart on the screen, how far from the slits should we place the screen? So I'm going to just sketch the setup right here. So I have two openings that I'm illuminating with my green light, and we know that they are 7.7 micrometers apart. And so light that comes through here is going to form an interference pattern. The light waves that make it to the center of a screen over here are going to be because the light traveled the same distance, so there's going to be a bright spot in the center. And then a little bit both above and below we get another bright spot, and that's where light travels one wavelength further from one of the openings than the other. A little bit up higher there's another bright spot, and it's the third bright spot that this problem is asking us to focus on. So we're thinking specifically about light going to this spot from the two openings. And this is the third order bright fringe because we start our ordering number with 0 there in the center. So up here we are at the third order bright fringe. That means that the difference in path length right here must be 3 wavelengths. So this distance in this difference in path length is 3 wavelengths. We know this distance, and if we call this angle right here theta, we have a small right triangle of which we know the opposite side and we know the hypotenuse side. So from that we can write that the cosine of theta is going to equal the opposite, so that's 3 times the wavelength over the distance between the openings, which I'm just going to symbolically write as d for now. And that means that theta is the inverse cosine of that ratio. So the inverse cosine of 3, the wavelength 550 nanometers, so 550 times 10 to the minus 9 meters, and then the distance between the two openings, 7.7 micrometers, so 7.7 times 10 to the minus 6 meters. And we want to calculate that out, making sure that we get our calculator in radians when we do this. So the inverse cosine of 3 times 550 times 10 to the negative 9 divided by 7.7 times 10 to the negative 6 and if I do that I get 1.35 radians. If I do the same thing but do it in degrees, we find that the angle is 77.6 degrees. So obviously my drawing not quite to scale here. Question C, if we want the fringes to be 1.5 millimeters apart on the screen, how far from the slits should we place the screen? Well, geometry-wise, if we trace the distance from the slide over to the screen, that's very often called the separation, L. And then if we trace up to this point, this angle is approximately the same as the other angle, very close given the geometry and the relative distances in this setup. We then know another right triangle where this distance is y, and this distance is L, and then here is theta. So if we want the fringes to be 1.5 millimeters apart on the screen, then this would be 1.5 millimeters, this would be 1.5 millimeters, and this would be 1.5 millimeters. So we can write the tangent of theta is going to equal y over L. We're solving for L, so L is equal to y over the tangent of theta. We want y to be 4.5 millimeters, or 4.5 times 10 to the minus 3 meters. And here we're using the tangent of our angle. You can work in radians or degrees. For this, it doesn't really matter. So if I take the tangent of 77.6 degrees, inverse of that, times 0.5 times 10 to the negative third, I get a distance of 9.89 times 10 to the negative fourth meters. So that is, on the scale of things, very close to the screen. But again, with this big angular deflection, my picture is not to scale. 77 degrees would be heading up at a pretty dramatic angle, so this would need to come in really close in order to get this spacing to be down to be 1.5 millimeters apart on the screen. Second problem says in a double slit experiment, the distance between slits is 5 millimeters and the slits are 1 meter from a screen. Two interference patterns can be seen on the screen, one due to light of wavelength 480 nanometers and the other due to light of wavelength 600 nanometers. What is the separation on the screen between the third order bright fringes of the two interference patterns? So 480 nanometers is on the bluish side of the spectrum, and 600 nanometers is on the reddish, and I've got a red pen and a blue pen. I'll take advantage of that. So I got my two slits. They are 5 millimeters apart. They are 1 meter from the screen over here. And I get two patterns. So the blue, the 480 pattern, there's going to be a bright blue spot in the middle, and then some blue bright spots off to the side there. The red is also going to have a bright spot in the middle, but because it is a higher wavelength, the fringes get spaced out more. And I might be exaggerating this too much, but something like this. And we want to know what's the separation on the screen between the third order bright fringes of the two interference patterns. So again, both at the center is 0. So 1, 2, 3. This is the third order blue. 1, 2, 3. This is the third order red. I'm looking for what this distance is right here. Well, given that the screen is a meter away and knowing what I know about light of these kinds of wavelengths, this spacing is going to be extremely small relative to the meter, which means all the angles that we're dealing with here are pretty small, which means we can go ahead and use the equation that combines the geometry based on looking at the path separation and also the slit separation from the screen. And we've shown elsewhere that that spacing is the number of fringes times the wavelength times the length over the distance between slits here. So this means I'm looking for the third order space from red light minus the third order space from blue light. So that's going to be m times the lambda that is red over the length divided by that distance minus m times the wavelength that is blue, L over D, and we can simplify that a little bit because m's going to be the same. It's 3 for both. L's the same. D's the same. The only thing that's different here are the wavelengths. And now we just need to plug in. We have 3 for the order. The length is 1 meter. The distance is 5 millimeters, so that's 5 times 10 to the minus 3 meters. And the difference in wavelengths, the red is 600 nanometers, so 600 times 10 to the minus 9 meters. And the blue is 480. And we can go ahead and calculate that out. And if we do so, that comes out to be 7.2 times 10 to the negative 5th meters, or I guess that would be 0.072 millimeters. So a very small distance that we're talking about here, and it might be hard experimentally to actually visually observe that. One way you could make that more apparent is pulling this screen further back from the slits, which would increase this separation distance when you do so. Problem 3, does the spacing between fringes in a 2-slit interference pattern increase, decrease, or stay the same if the slit separation is increased, if the color of the light is switched from red to blue, if the whole apparatus is submerged in cooking sherry, if the slits are illuminated with white light, then at any side maximum does the blue component or the red component peak closer to the central maximum. Well, again, broadly the geometry for these situations is that I got a screen somewhere over here. I have 2 openings that are pretty close to each other, and then the light traveling through those to the center of this opening produces a center bright spot, and then off to the sides I get these other maxima of intensity. In between is dark on that pattern, but that spacing between bright spots is generally labeled with a Y. The distance between the slits and the screen is L. The distance between slits here is D. And then we're usually looking at some angle when we're off at some point. But if the angles are relatively small, again, we've shown elsewhere, we can combine equations and find a relationship that predicts the fringe spacing based on all the other factors. And it looks like this. So let's use that to actually run through these things. If the slit separation is increased, well, if the slit separation is increased, then D is increased, which leads to Y being decreased. They are inversely proportional to one another. If you pull this away further, then these distances between bright spots shrinks because it doesn't take as much of an angular deflection to get 1 wavelength, 2 wavelengths, 3 wavelengths of path difference. If the color's light is switched from red to blue, so if the color of light is switched from red to blue, red has a relatively higher wavelength, blue has a relatively lower wavelength, so the wavelength would be decreased going to blue light, which would mean the spacing between fringes is decreased as well. The whole apparatus is submerged in cooking sherry. Well, if you dump this all in cooking sherry, I'm not sure why they chose that particular liquid, but any liquid is going to have an index of refraction that is lower than the index of refraction of air, and we've shown elsewhere that the index of refraction, which is the ratio of the speed of light in a vacuum to the speed of light in some medium, can also be written as the ratio of the speed of light in a vacuum, or the wavelength rather of light in a vacuum over the wavelength of light in whatever medium. Air is pretty close to a vacuum in terms of the optical properties. So what this means is if I make the index of refraction higher by throwing this thing in cooking sherry, the wavelength has been decreased of the light. And if I make the wavelength of the light in this region decreased, I'm going to observe the same effect that I did by changing the color of the light. Finally, if the slits are illuminated with white light, then at any side maximum, so a side maximum over here, not the center, does the blue component or the red component of the peak closer to the central maximum? And again, because the wavelength of blue is shorter than the wavelength of red, then that means the blue component on these spacings are going to peak closer to the central maximum. And we showed that on the previous problem as well, which means, by the way, if you try to do this experiment the original way that Young did, which is my understanding with white light, it's really hard to interpret the results unless you get really good color vision, because right here in the center you'll get a maximum bright spot and it'll be white, but then the peaks of all the constituent colors that make that white light occur at different locations, and so largely you're just going to see this light kind of spread out with different colors being dominant at different areas. And at least for a person like me who's red-green colorblind, that would be super challenging to figure out what's going on in terms of the double slit interference. It's much easier with what we do these days, which is to use light with a single wavelength like laser light when we're doing that experiment. Then we looked at some thin film problems. This is white light on a film. White light is sent downward into a horizontal thin film that is sandwiched between two materials. The indices of refraction are 1.8 for the top material, 1.7 for the thin film, and 1.5 for the bottom material. So I've got some layers here. And what's going to be important here is that the top one has an index of refraction of 1.8. The middle layer has 1.7 and the bottom has 1.5. The film thickness is 5 times 10 to the 7th meters. And of the visible wavelengths, which are in the 400 to 700 nanometer range that result in fully constructive interference at an observer above the film, which is the longer and which is the shorter wavelength, the materials of film are then heated so that the film thickness increases. Does the light resulting in fully constructive interference shift toward longer or shorter wavelengths? Now, light is incident upon this sort of sandwich of layers, and there's lots of things going on, but we have light that comes and hits the boundary right here, and part of that light is reflected at the boundary. Part of that light keeps going on into the layer. Part of that is reflected here. Part of that's retransmitted out in the top. And this keeps going. You get more reflection here, more transmission here. But in order to understand what's happening here, we need only to focus on these two parts of the light wave that come out first. The one that's reflected off of the top boundary and then one that's been reflected off of the bottom boundary in the process. We also need to, in these thin film problems, think about the relative indices of refraction at each of these layers. Because you're going from a medium where there is a high index of refraction and bouncing off a medium where there is a relatively lower index of refraction, that is akin to free end reflection, and there is no phase change that happens at that top boundary. Similarly, down here, you're going from a material that has an index of refraction of 1.7 and bouncing off a material that has 1.5. So there is no phase change in the reflection event off of the bottom as well. Okay, so really, this light that goes down through the layer and travels back up has traveled some extra distance, and we need that extra distance to be a whole number of wavelengths if we're searching for constructive interference. So the path length difference is the distance traveled by beam 2, let's call this one beam 2, relative to the distance that beam 1 traveled. Well, beam 2 traveled down a thickness t, no phase change, and traveled back a thickness t. So the distance it traveled was 2t. Beam 1 had no phase change, so to this point, the distance it traveled was 0, just reflecting off of that surface. And so the difference in path length is 2 times the thickness of the film. But that, for constructive interference, has to be a whole number of wavelengths. So it could be 0, but then, of course, the film has no thickness. Or it could be 1 wavelength, or it could be 2 wavelengths. Whoops, getting too many commas in here. 3 wavelengths, etc. Which means that the wavelength of light, then, is going to be 2 times the film thickness divided by some number. And since we've already said 0 makes no sense, I'm just going to call this a general n, where n is 1, 2, 3, 4, etc. Okay, 2 times the thickness of the film is 1,000 nanometers, since each thickness of the film is 500 nanometers. And so we can just start saying, okay, 1 wavelength possibility would then be 1,000 nanometers divided by 1, so 1,000 nanometers. 1,000 nanometers divided by 2 would be 500 nanometers. Divided by 3 would be 333 nanometers divided by 4, 250 divided by 5, 200. Probably don't need to keep going on from here. And from right here, it'd be tempting to say, oh, we got our answers here. It's 500 and 333. Except this is the wavelength in the film, and the 400 to 700 nanometer range is the wavelength of visible light in air. And so we need to do some translation. So recall that the index of refraction is the wavelength in a vacuum, but in this case it's going to be in air. That ratio of that wavelength in air to the wavelength in film, which means that the wavelength in air is going to equal the wavelength that we had in film times the index of refraction. So now we got to do a little bit of translation. The index of refraction is 1.7. So if we find these equivalent indices, or wavelengths rather, in air, this one would translate into 1700 nanometer wavelength light, which is outside of that visible range. 500 times this would give me 850 nanometer light, which is also outside the range. But 333 times 1.7 is 566 nanometers. 250 times 1.7 is 425 nanometers. 200 times 1.7 is 340 nanometers. And there's my 2 candidates for actually being able to see the thin film interference effect in this particular thin film. So 566 nanometers, which is sort of between green and red, maybe an orangish part on the spectrum, and 425, which is down there near the blue and purple. Which means if I looked at this layer, I would see those colors sort of strongly reinforced and other colors like red and yellow being canceled out in that reflection event. There's a third part of this question. Does the light resulting in fully constructive interference shift toward longer or shorter wavelengths if the material was heated? Well, there's sort of a lot of things embedded in that property, because we're assuming that when we heat this and the thickness increases, that doesn't increase the index of refraction here. And I'm not entirely convinced that would be the case, but let's go with it because we have no other model to accompany that. So if we have this relationship here with the wavelength, so if we heat something and something becomes more thick, then this distance is greater, which means the wavelength that produces fully constructive interference also gets greater. All of these numbers would be greater. Our final answers would also be greater. So the answer to C is that it shifts towards longer wavelengths if the thickness of the film increases. Problem 5 is about coating. We wish to coat flat glass with a transparent material so that it will reflect light at a wavelength of 650 nanometers, and that light is illuminated by interference. What minimum thickness can the coating have to do this? So let's go ahead and sketch out this situation. So I've got air up here, which has an N of about 1. I've got some coating, which I've chosen with an index of refraction of 1.25, and then down here is glass. So this might be, the physics behind making glasses. For those of you that wear glasses that have anti-reflective coatings, you can coat the glass so that certain kinds of light are eliminated by interference through that reflection event off of that glass. Okay, so what minimum thickness can the coating have to do this? Well, again, let's think about what's going on here. I've got light coming in from the air, reflecting off of boundary 1. Some of that light, though, continues into the coating layer and then is reflected off of the coating glass boundary. Some of that goes back out into air. Again, more of the light keeps going in other directions, but we're just focusing on these two pieces of the light wave that came out. And thinking about what happens at each boundary, since we need to work out how much longer the path is for the piece of the wave that's number 2 as opposed to the piece of the wave that's number 1. Well, here if I hit off of air on the coating has a higher index of refraction than air, so that means there is going to be a phase change at this boundary. It's just like a fixed end reflection when you do waves on a spring. Here as well, coating to glass is the higher index of refraction, so there is also going to be a phase change here, and we need to keep that into account when we are working out what the path length difference is. So the path length difference is just the path of wave 2 minus the path of wave 1, and we're looking for the relative distances, so we don't care about the total distance, just the extra distance in effect that 2 travels. So 2 travels in here, travels 1 thickness of the layer through the layer, has a phase change, which is like a half wavelength of travel. So it travels a thickness T plus a half wavelength plus another thickness T, and it emerges back out into the air. 1 doesn't travel any thickness of the film, but because of the phase change, it's the same as traveling an extra half wavelength. So its distance is effectively a half wavelength. But those 2 phase changes are in a sense going to wash each other out, and the total path length difference between 1 and 2 is again 2 times the thickness of the film. I want destructive interference, so I want 2 times the thickness of the film to give me half a wavelength of extra distance, or 1.5 wavelengths, or 2.5 wavelengths, all of the conditions for destructive interference, which is an integer plus a half number of wavelengths. But if the thickness is going to be the smallest that it can be, we're going to go ahead and select the condition where it is a half of a wavelength. And so if 2 times the thickness equals 1/2 of the wavelength, that means the thickness equals 1/4 the wavelength. But again, this is the wavelength in the film, and the wavelength in the film is equal to the wavelength in the air divided by the index of refraction of the film. So that's 1/4 the wavelength in the air, which is where we assume the light's coming from at 650 nanometers, divided by the index of refraction of the film. So if we plug that in, we have 1/4 of 650 nanometers. Not going to bother changing the units on here since I only have one thing that has units. The thin film has a index of refraction of 1.25, and if we calculate that out, we get 130 nanometers. Again, this would work if it was 1.5 wavelengths, but that would make the thickness greater, 2.5, etc. So you could make coatings that are thicker and still achieve the elimination by interference effect. But for most applications, say you're coating a pair of eyeglasses, you want that coating layer to be as thin as possible. Finally, a question that is akin to the physics of old glass. I don't know if you've ever been in a building with old glass windows, but they actually, since glass is a super slow flowing liquid, over time, enough time, dozens if not hundreds of years, the glass actually flows and the bottom of the window becomes thicker than the top of the window. So this is a thin film. It doesn't say it was glass, but the width increases downwards because gravitation causes slumping. And then figure B is a face-on view of the film. So if you took this film and you turned it and you looked at its face, you would see a series of bright spots, dark spot, bright spot, dark spot, bright spot, dark spot, etc. Points in the cross-section corresponding to bright fringes are labeled A, B, C, and D. So in terms of the wavelength of the light inside the film, what is the difference in the thickness between points A and B and between points B and D? Well, let's go ahead and kind of make a bigger sketch of that wedge so that we can talk about what's happening here. Again, I'm going to then have, let's see, air and then some film, which I'm going to assume has a higher index of refraction than air, and then air on the other side. So I'm going to get light that comes into this layer. Part of it gets reflected off and travels back in the air. Part of it goes through the film, reflects off the other side of the film, and then comes back in into the air. And again, there's many more events that are happening here, but we're ignoring them and just focusing on the first two reflection events. So this is wave portion 1 and wave portion 2 to be consistent with what we've done before. And we are focusing on the path length difference, how much further 2 goes than 1. So let's think a little bit about the boundaries. So right here, air, film has a higher index of refraction than air. So this reflection event does involve a phase change of 1/2 of a wavelength. But on this side, when you are bouncing off of the film-air boundary, because air has a lower index of refraction than film, there is no phase change that happens on this side. We're looking for a path length difference between wave 1 and wave 2. So 2 comes here, travels whatever thickness the film is at this point, so that is T, doesn't have a phase change, and then goes back, so it travels a distance of T plus T. 1 doesn't travel any extra distance through the film, but because of the phase change, that's effectively like moving a distance of 1/2 of a wavelength. So the path length difference here is 2T minus 1/2 of a wavelength. We're focusing on the bright fringes. In the color version of this, these are red, but we've got grayscale here. And so if we're focusing on bright fringes, the condition for constructive interference is that this path length difference has to be some whole number of wavelengths. So I would have 2T minus 1/2 of a wavelength has to equal some number of wavelengths where m is 0, 1, 2, 3, etc. So we want to know, in terms of the wavelength of the light inside the film, what is the difference in film thickness between points A and B and between points B and D? We don't know what the path is at A, but we do know that if A involves moving through the film, let's say the thickness of the film ends up being, oh, I don't know, something like 17 wavelengths. Well, actually, let's solve this for T, because we need that half in there. So 2T equals some number of wavelengths plus a half a wavelength. And that means the thickness is ultimately some integer number plus a half number of wavelengths divided by 2. Well, so if where A was, m was 17, the distance at the next point where B was, m would be 18 to meet this condition. And so because of this 2 down here, the difference in the path length is going to be a half of a wavelength. Let's make that a little more concrete. Let's say I had, this was 17 and this was 18. I should have picked easier numbers to do math with, but we'd write 18 plus a half number of wavelengths over 2. That'd be the thickness at B. And then we'd be subtracting 17 plus a half of a wavelength divided by 2. This part would go away since it's the same on both sides. And I'd be left with 18 halves of a wavelength minus 17 halves of a wavelength, which would be 1/2 of a wavelength. So between consecutive bright fringes, they would be 1/2 of a wavelength difference. B and D skips C in here, so because B and D are separated by another bright fringe, the difference between B and D would be a whole wavelength of the light. So those are the problems we looked at involving light interference. Please let me know if you have questions, and as always, if you spot errors in the solution, I'd appreciate you pointing that out. Thank you.